Sreemanta Mitra. I belong to the physics department of GITAM University's Bangalore campus, and I did my PhD from Cultivation of Science, Calcutta. The degree was awarded by the University of Calcutta. I worked on the experimental physics, experimental condensed matter physics. Later I moved to, after graduating, I moved to Weizmann Institute of Science in Israel, and subsequently I went to the Nanyang Technological University in Singapore. I came back to India and joined Indian Institute of Science as a research staff and worked there for 3 years before joining to GITAM as an assistant professor in 2022. Presently, I am working on developing a set of systems based on the van der Waals system. So 2D materials are my areas of expertise, which I would like to explore as well. Alongside, I am trying to developing a system of materials based on these 2D materials known as the van der Waals heterostructures. I generally try to explore different types of materials and then combine them to create a new material system for studying the fundamental aspects. Alongside this fundamental aspect, there are several technological aspects of these materials. This quantum materials has a big throughput in the national quantum mission, which has been recently announced by the government of India. I have a plan to link my research towards the possibilities of quantum computation, quantum key distribution and quantum cryptologies, and along this direction I would like to extend the knowledge or the expertise around the materials and related stuff to connect back to this direction for better technological aspect. So during my PhD, I was working on two-dimensional system, which I extended on graphene and graphene-based nanocomposite systems. I studied the electrical transport, magnetic measurements, as well as some optical measurements in those systems. And later in Weizmann, I was working on quantum phase transition in amorphous superconductors, and that went on for a couple of years. And then in Singapore I was working on the transport properties in single crystalline material, which is a rare earth tetraboride. In India, when I came back, I started delving into the 2D systems again, explicitly in 2D semiconductors, graphene, MOS2, and studying their light matter interactions. Essentially, I learned the technique of developing a new set of material system, which is known as the van der Waals materials and their heterostructures. So I can engineer materials based on this 2D layered system. So all my efforts were in the direction of exploring the fundamental physics and fundamental physics of the electronic systems, which includes different semiconductor, superconductor, metal, and all these sort of diverse areas or diverse aspects of materials. Recently, my research has been funded by the Science and Engineering Research Board, Department of Science and Technology, Government of India, and also a part of my research is generously funded by the university. Also recently being selected as a multi-faculty fellow. I got some more funds from the university to carry out my research in this direction. I'm establishing my new quantum materials and devices lab in GITAM Bangalore. All the instruments are coming. Please do check out our website for a better reach. Feel free to connect back to me or to anyone in the department to join us. We always look for prospective people to join our journey towards this direction. We have masters as well as the undergraduate courses that runs in the department, as well as we are having the PhD programs of the university. The intake is twice a year. It generally happens in June and December. And we also have the opportunities for the people to join us as the research intern. Please look out for the opportunities in the social media platforms, and we are always looking for bright and motivated people to join us in every other aspects to carry out more meaningful research. So in my lab we are basically trying to explore the emerging phenomena in quantum materials. I worked on basically more concentrating on the 2D material systems, and also I have the efficiency to make the engineered quantum materials by putting layers of different 2D materials into consideration. Then the next thing is that we do perturb the system by various means to explore the different applications of that materials. One of the key areas of measurements that we usually consider is the quantum transport and light matter interaction and optoelectronics. So we are evolving in that direction. In the next one you can see our research effort to understand the light matter interaction in few layered phosphorus, black phosphorus, which is a very interesting material for potential applications in electronics and optoelectronics. So this is a collaborative effort between various faculty members in department and some people from the other institutes. Let's have a look inside the lab. From our side is to generate the single layer or the few layer of the van der Waals materials, and we employ two techniques basically to reach to that level of single atomic layers. One is Scotch tape technique, which is like mechanical exfoliation. The van der Waals materials are the materials in which I am interested currently, is a layered materials in which the layer of different layers are arranged in a particular direction, and they are attached with a very weak van der Waals force. This is the exfoliation table. We would call it an exfoliation table, and you can see the Scotch tape hanging around, so we have the efficiency to peel off single layers of various materials. Can go until the single layer, of course. So the beauty of these materials is that they have the strong in-plane interactions between the atoms. So it's very strong in this direction, but very weak in this direction. So we can take it off and we can get to the single layer, which is very strong in the XY plane, I would say. So once we fabricate that material, we come to our first hand of understanding of that material using the optical microscope. The optical microscope is a metallurgical optical microscope, and it is a trinocular one, so it has a camera attached to it which directly feeds the image to the computer, and we identify the flakes based on which we choose which one to use and which one not to be used, which one should throw. The other aspect of our direction is the liquid phase exfoliation. So we disperse this van der Waals materials into liquid, and then we apply an ultrasonic wave to break out that bonds, that's van der Waals bonds between the layers to reach to the monolayer. So we have an ultrasonic system in which we can provide the ultrasonic wave to the systems to break the bonds. So we have other instrument which is a hot plate and magnetic stirrer, which is a very standard laboratory equipment, and so that has various purposes to stir the materials. It can be used to heat certain things to a reasonable temperature. The next thing, once you have this liquid phase exfoliated samples, you can choose to make a device out of it, and that device can be made in the form of a thin film, and that thin film is can be made using various techniques. So what we are trying to do it in our lab is to develop a technique to make the thin films of these liquid phase exfoliated materials, or the arrangement of the materials using a deep coating system. So that is a deep coating system where you have that material, exfoliated materials dispersed in a liquid, and you have this control which you can put inside and take out that to make a film of that onto the substrate. The newest addition to our group is to have this nice little thing which is known as the transfer setup. And the transfer setup is allowing us to make van der Waals heterostructures of different van der Waals materials. For example, if I say you like MOS2, which is the molybdenum disulfide, and graphene are two van der Waals materials, and we have the facility to take single layers out of it, and now we have the efficiency using this instrument to put one on top of each other. The interesting thing of the van der Waals heterostructure is that they are not limited by the lattice parameters of any particular system, because essentially they will be connected by the van der Waals force and apparently floating, you can say it's like floating on top of each other. Even if they are not touching each other, there is no physical contact between these atoms of layer 1 and layer 2, the proximity is going to introduce a lot of changes into the electronic structure of either materials, which we can use and probe and to find potential applications for that. We also have the feasibility using this system is to rotate one layer with respect to other, and that rotation will create interesting patterns if you look into the crystal structures of that system, and that leads to very interesting fundamental physics. For example, two graphene layers, if they are rotated by a very very small angle, it's like one degree or so, you can create entire spectrum of the electronic structure. You can have a Mott insulator in one side, you have the superconductivity on the other side, and you can have, just by rotating at a particular direction, which people usually called magic angle, and that has been developed recently, very very recently, in I think 2018 by MIT physics group, and many people are trying to exploring that. And so we are also envisioning ourselves to explore that. So once we fabricate the device, we'll get it to the various collaborations that we are having to make the nano devices out of it. That's including the electron beam lithography that is available in very near, like 40 kilometers from us, in the Indian Institute of Science, where I used to work. And I got the training for utilizing all those instruments, and I have also the collaborations who can actually make sure that these devices can be formed. And once we make the devices, we take it back to our lab, and we aspire to study their various properties, including the light matter interaction and the transport properties. So one of the instruments for measuring the transport properties is already here, which is a DC voltage source, and this also measure the resistance of the sample. So we are in the process of making a low temperature system where we can cool down the devices at very low temperature. That is a collaborative project with another faculty of the department. And we are trying right now developing this technique inside in GITAM to be able to measure things at very low temperature, the transport, and also we in the Murthy lab we are supposed to get a Raman spectrometer and the photoluminescence spectrometer. In the department we are also expecting FTIR and many other instruments to come up in very recent time. So we are in the process of developing a vibrant research ecosystem in GITAM, especially in Bangalore. And we expect you to join us, and we will explore it together with you. Feel free to write back to us. Thank you.
GITAM University has the legacy of more than 40 years. Out of the 3 campuses, which happens to be in Vizag and Hyderabad and Bangalore, we belongs to the Bangalore campus. So Bangalore is the newest campus, established in somewhere in 2012. And I belong to the physics department of the GITAM University, and we have 4 specific units as per the research is concerned, which includes condensed matter, photonics, radio and atmospheric science, and theoretical physics. And we have several interdisciplinary works going on amongst these 4 units, and we basically have 16 faculty members working on the diverse areas of physics and doing cutting edge research.
In GITAM Bangalore, we have School of Science, School of Technology, School of Humanities and Management. I belong to the School of Science. School of Science has 4 different departments, including Department of Physics, Chemistry, Mathematics and Biological Science. The Physics Department is having 16 faculty members who work on the diverse areas, including condensed matter, photonics, and radio and atmospheric science, as well as in theoretical science, which is a broader discipline. In GITAM, alongside the standard educations, we have keeping up the research infrastructures and in the campus. We are generously funded by various funding agencies of the Government of India. As alongside, the university is putting a lot of effort and money on these directions. Right now, we are mostly concerned in developing the fundamental science and applied sciences infrastructures. We recently have a very dedicated specialized lab known as the Mitra lab for doing cutting edge research in diverse aspects.